So, Professor Samarth, the floor is yours.
Okay, thanks, Sushmit. So first of all, here's the outline. So I'll give you first an overview of the epitaxial quantum materials that we've been developing at Penn State. And then I'll choose a few examples that have come out recently. The first two have come out from this consortium facility, and the third one is something that's just emerging from one of my own MBE systems, and where it may not be obvious that consortium on metrology, particularly for quantum anomalous Hall effect, that interfacing topological semi-metals with ferromagnets, it's not obvious that it's immediately of interest to you, but I'll try to explain why, in general terms, it might provide an interesting pathway. So, you're all aware, of course, of the various solid-state platforms that people are interested in broadly in the, for quantum technologies. And a few years ago, I had collaborated with some colleagues on this article, sort of trying to aim at material scientists, trying to get them interested in what are the materials opportunities and challenges for developing materials for quantum technologies, whether they be superconducting circuits or quantum dots or topologically protected systems or color centers and so on. So in this context, my group's goal is to develop quantum materials configurations that are broadly aimed in this context. I'm interested in spintronics, quantum sensing, metrology, as well as trying to develop platforms, condensed matter platforms that could eventually be used for some kind of topological quantum bit. I mean, we are not in that, certainly not mainstream players in that field, but we are trying to just invent new materials that could be interesting in that context, right? So in my group, let me just give you a sense of what's going on. So there is a big emphasis in my group on topological states of matter. So we are looking at topological insulators, topological semi-metals, and anything that has topology in its band structure playing a dominant role. And we've been trying to use some of these topological characteristics of the band structure for applications. And these are applications are just room temperature applications of spintronics. I have a continued interest in developing materials where one tries to use the spin textures either in the momentum space or real space for memory applications, for example. As part of a completely new thing that I started doing in the last some years, I'm part of a big DOE center here that's centered at Argonne National Labs and at University of Chicago. It's headed by Dave Avshalom, and in my own group, we've been interested in NV centers in Diamond for magnetometry, but also more recently looking at superconductivity in Diamond, and eventually aiming to make, we're in the process of making Josephson junctions and making interesting hybrid structures in my group based on Diamond that we grow at Penn State, and then learning how to process and so on. And then finally, with a junior colleague at Penn State, I've been developing multi-terminal Josephson junctions based on graphene. And we're trying to pursue multi-terminal Josephson junctions as a platform for modeling topological systems, but also for going after some non-Hermitian physics and so on. So what I'm going to focus on in this talk, which I thought would be relevant, to how I hope to interact with your consortium, is really on the topological sort of materials. And forgive me, we're all experts here, so some of these slides are slides from other presentations, and so you forgive me about the sort of introductory nature of some of these things. But we're all aware of this, what Xiaogan Wen in his Reviews of Modern Physics article referred to as the topological zoo. And many of us, I think, on this call have been interested in materials with topological band structures, whether they be topological structures on the surfaces or in the bulk, such as in Dirac semimetals, and so on. And these are all, of course, as you know, due to the various interplay of symmetries and spin-orbit coupling and so on. And so, these, because of the correlation between spin and momentum, they have had proven impact on spintronics. I mean, we have, I've had funding with industrial partners where there is a very strong interest in memory applications, for example. As you all know, in your consortium, these are, of course, really pertinent for metrology, some of these materials, like quantum Hall insulators and quantum anomalous Hall insulators. And I like to say that they're of aspirational interest for topological quantum computing. So hopefully sometime we'll get a topological quantum bit. So what I want to spend time on really is describing the facilities that we have. So some 8 years ago, the National Science Foundation put out a call for an unusual kind of facility that they wanted to fund. And this is called the Materials Innovation Platform. The idea was that, well, in physics, we have all these grand facilities like synchrotrons and the national, high magnetic field labs in various countries. And even though there are some places like in Berkeley, the Molecular Foundry, where you can go in and use a facility to synthesize materials, this was really lacking across the board, right? So the idea of the National Science Foundation was, is there a group of people crazy enough to, put together a facility focused on synthesis, where the goal is not to carry out simply research that is in-house, but really to serve it, to provide a service to the community. And we were one of two groups that got funded to do this. So Daryl Schlom at Cornell was one of the groups, and then myself and Joan Redwing and Vin Crespi here at Penn State, we were successful. And the consortium we put together is called the 2D Crystal Consortium. This is just one part of the facility. This is a CN to Omicron, sort of a cluster tool, if you will. It's got an MBE system with all the sources that I've listed over there in red. It's got an RPES capability with a good resolution. We also got we've got a helium lamp excitation, but also an yttrium fiber laser for doing additional photon energies at low energy. And then we have an LT Nano for doing 4-probe measurements. It was supposed to be also an STM. It is an STM, but it's a pretty lousy STM, honestly. I'm hopeful St. Omicron is not on the call, but it works beautifully as a 4-probe in situ measurement tool. And as you can see, for example, so with this kind of facility, we've looked at iron selenide with in situ probing of the superconducting transition in iron selenide. That's down here. And then we've looked at RPES. Now you might wonder, where is cadmium arsenide coming from? There is no cadmium on arsenic, and I'll show that on the next page. But the key thing is that for the US, institutions in the US, this has provided a facility where users can come in, they can submit proposals to either get samples from us in close collaboration, or they can come in and grow samples themselves. And it's been extremely successful. So we have users from, East to West Coast. We also have users in this facility who've come from outside, but in that case, they actually have to, pay. It's not free. For US users, it's completely free. This is not the only part of the facility. We also have an additional MBE system that was initially set up by Homan Engel Herbert, but now it's run by Stephanie Wissel after Homan went to Germany. And it's also got my own MBE systems, which are a couple of VICO systems. And here's where we grow cadmium arsenide, tantalum arsenide, and so on, as well as quantum anomalous Hall insulators. It's sort of dedicated towards that. And via vacuum suitcase, we can go in and use these characterization tools. Okay, so let me just pause here for a minute. I know we'll have talk later. We'll have time again to talk later on. But in case there are any urgent, pressing questions about how such a facility operates or so on, I'd be happy to answer them now or later. So feel free to interrupt if you think you have something, and just just yell. Okay. So this facility now is in its second phase, and we have 2 more years to go. And then beyond that, we are discussing, how to also keep it sustained. But it's going to be an important. It's going to play an important role. Now, what kind of materials have we produced from this facility? Well, here's some examples. As I said, we've been very interested in spintronics. So the idea of taking a ferromagnet, interfacing it like ferromagnet, like cobalt iron boron, interfacing it with bismuth selenide. We've done 2-dimensional ferromagnets like chromium ditelluride, and interface them with Dirac semimetals like zirconium ditelluride. We've, in my own MBE system, we've also grown Dirac semimetals like cadmium arsenide. And then, a very strong component of our research, of course, are churn insulators or quantum anomalous Hall insulators. But we've sort of been taking that beyond the conventional idea of simply growing a quantum anomalous Hall insulator. So how does this fit in with everything you guys are doing? I mean, I do not work in metrology. We have one project right now with our with a group at NIST. As you know, quantum Hall effect, Josephson effect are something that are of key interest to all of you in terms of metrology. But we have a 2DCC, in 2DCC, we have a vested interest in exploiting other topological phenomena. And these other topological phenomena, of course, is the, aimed at the precise measurements of the Planck constant and so on, is, what you guys are working on, right? The churn insulator. So again, my apologies. These are introductory slides that I didn't have time to just remake for this. But as you know, the idea of the churn insulator in the context of quantum anomalous Hall effect is to take a topological insulator, magnetically dope it, so break time reversal symmetry, open up a gap or introduce a mass, if you will. And this was predicted by the late Shucheng Zhang and his group, and then discovered by someone who's now my colleague, Suizhu Chang, and his advisor at the time, Chiken Shui. And of course, in your consortium, this is one of the important players, I'm assuming, in terms of doing electrical metrology at zero magnetic field. The result I'm showing here on the screen is one of the very, very early measurements where we were still, this was with Fuanong and Ali Asdani at Princeton, where we were far from where you guys are right now. But, it started only 8 years ago, right? I mean, 8-9 years ago in terms of seriously pursuing how accurately can you see quantized anomalous Hall effect. And here I've listed on the right-hand side, and again, it may be that I'm not aware of some of the very recent stuff that's gone on, but there was a lot of focus at Stanford and PTB and Würzburg and in Japan on doing metrology with these chromium or vanadium doped bismuth antimony telluride materials. And then the Japanese group figured out that instead of uniformly doping, you could do sort of modulated structures. They use the unfortunate term of modulation doping. Those of us who are in semiconductors, it's a bit irksome because putting chromium or vanadium in one region of the sample and not in the other is not modulation doping in the sense of what we are used to in semiconductors. These magnetic dopants don't provide carriers that go into the undoped region. But okay, we'll stick to that term. So, there with this modulation sort of doping method, people have improved things quite a bit, right? I do recall a talk, I think, at the March meeting from the Würzburg group. This is Marcello Jaime, um, at the last March meeting, where I believe just with uniform vanadium doping, they were also getting really good, accuracy. Uh, so the questions to me as an MBE grower are, what is it that you guys need? And this is honestly the question that I would like to address at the end in the discussion session. What is it that really limits the precision of these magnetically doped chalcogenides for metrology? And to me, the big question is it intrinsic physics? I mean, you go and talk to a theorist, and they'll tell you that, oh, the reason your sample is not is showing some dissipation is because you're scattering into some other kind of helical states, or there is an impurity band or something like that, or is it simply extrinsic factors such as disorder? So my question is, are MBE grown materials at a stage where we can go to a theory colleague and say, give me a rational design principle, to make a sample which has a large energy gap so that your topological states are protected, and you can get to the precision you need for your metrology experiments, right? And my take on this is that the theory in this case is far from really helping us. All these nice ideas about scattering to this and that in terms of band structure, it doesn't work, honestly, and this is because I think Lawrence and I are probably one of the only two MBE growers who will provide in slides, statements like our samples are actually not that great. It's so the Drude mobility of the samples that we make that provide what I would call decent quantum anomalous Hall effect are rarely better than a few hundred centimeters squared per volt second, right? We routinely do X-ray diffraction as a way to measure the structural characteristics. And unlike the gallium arsenide samples that I make, where I can honestly say I'm making high quality gallium arsenide, here I cannot say I'm making high quality MBE grown samples, right? And the other thing is that when you guys who are not growers, when you go and read our papers, the field has unfortunately been a little bit lax in terms of providing MBE growth details. So, for example, I have to admit I'm also guilty of this. Like, if you read some of our papers, you'll see that we don't give you the bismuth antimony composition or the chromium composition. We simply say chromium doped bismuth antimony telluride, and leave it up to you to go and dig through all our past papers and figure out, what are you talking about? What if I want to grow build an MBE system for the consortium and provide materials, a brand new system? What parameters should we aim at, right? So there has to be some kind of standardization of MBE growth protocols, sample characteristics. The Molenkamp group, my group, Tokura's group, the group at UCLA, we all use different substrates. So Molenkamp, I think Lawrence has been, and Charles Gould and company have been growing on silicon. Very often the Tokura group has been growing on indium phosphide. We use strontium titanate. The Kang Wang group at UCLA uses gallium arsenide. Does this matter? So each of us in our own sphere, in our own little domain, tweak our MBE parameters and so on to get some characteristics, right? But how do we get standardization? I mean, this is the kind of thing that I hope your consortium, will help us resolve, right? Because it's hard for us, it's hard for me to determine, are my samples good enough for you or not? Another thing that I want to point out is when I talk about structural disorder, the structural disorder also has an impact on the quantized behavior through how it affects the magnetism. So this is a paper it's 9 years old now, a beautiful paper from Weizmann Institute from Eli Zeldov and his group, where they took our samples and they wanted to look at the magnetism in the samples. And what Ellie basically, I didn't like the term he used. He calls it super paramagnetism. I like to call it strongly pinned ferromagnetic domains. But what Ellie showed was that, unlike all the magnetically doped semiconductors that we had been studying for years, which behave magnetically like good, well-behaved ferromagnets. How do they reverse the magnetization? Well, in a large sample, you get the propagation or expansion of domains. You get propagation of domain walls and expansion of domains. Here, when Ellie used scanning squid magnetometry to measure the evolution of the magnetic state as you reverse the magnetization, as you go from Chern number equal to -1 to +1, what he found was that the magnetization is strongly pinned. It's very inhomogeneous, and it's sort of little unconnected domains, if you will. Later on, Ellie looked at modulated heterostructures from Tokura's group, and things did improve. So the domains got larger, but nonetheless, the overall behavior was still the same. So, so what this brings up, of course, is here you have structural disorder, probably also is affecting the magnetic and electronic disorder, right? And one question that this brings up is when you guys are pursuing metrology and you want these topologic protected edge states or current flows in your sample, you ask yourself, where does the current flow? And of course, as you know, in the quantum Hall insulator, and this is again a slide that you're all familiar with, so I don't want to spend too much time on it, but you're all aware, of course, of the work that von Klitzing did a decade ago in the context of the quantum Hall insulator. And I don't know how broadly his arguments are accepted, but certainly I'm convinced that they showed at the time, that current doesn't just flow in the edge, right? So depending on whether you're at thermal equilibrium or away from equilibrium, under what conditions of bias you're operating your device and so on, that you do get flow into the bulk states of the sample, because there are incompressible regions that carry this dissipation-less current, and the incompressible regions can extend into the bulk of your sample depending on the conditions. And these are conditions that depend on the details of the sample. But nonetheless, you still preserve precise quantization. And this is at a fundamental level because I think of bulk edge correspondence. So it's, so the question now is, this question has been looked at in quantum Hall effect. What happens in a quantum anomalous Hall effect sample? And in the early stage of this field, several groups, including mine, we addressed this question. Groups like Suezu Chang and Moses Chan and Jagdish Mudera did the standard sort of thing that you do with non-local measurements and measuring a sample between different contacts and so on, and applying Landauer-Boutiker, and showed that, look, everything is consistent with Landauer-Boutiker, its edge states. In my own group, we studied the magnetoresistance as a function of the angle of the magnetic field. As you change the magnetic field angle from out of plane to in plane, and this anisotropic magnetoresistance, if you will, to use a term borrowed from the magnetism spintronics literature, we showed that you could explain this also, by using edge states. And then more recently, in Lawrence's group, they had a very nice paper based on the Corbino geometry, where they again showed a picture that, look, Landauer-Boutiker analysis of non-local measurements in these Corbino geometry disks of quantum anomalous Hall insulators is consistent with edge state transport. And in fact, they argued that the edge state transport persists even when you don't have quantization, all the way up to where the ferromagnetic phase transition occurs. But these are all interpretations, right? And so one of the users that we have at our facility, Katya Novak, she came to me and said, "Oh, I've developed this nice scanning squid magnetometer that operates at in a dilution fridge. Could we design samples to go after to look at the edge currents? I want to see these edge currents." And we said, "Sure, it should be a straightforward experiment." So Run Shao, my student, grew the samples, fabricated the devices, top and bottom gates and everything. These are nice devices. They're probably not at the standards that you need for metrology, but the quantum anomalous Hall effect is nicely quantized. The RXX dissipation is reasonably low, down to something like a few ohms or thereabouts. And then Katya and her student went looking, and of course the data they found was quite surprising. They saw, you can certainly see edge states, but when you are deep in the quantum anomalous Hall, the quantized regime, what their scanning squid shows is that there is current flowing everywhere, and it's complicated. There are swirls of current going into the into the middle of the sample, um, um, and so on. And it was just not what we expected. Now, I would strongly suggest that for this consortium, you really ought to have Katya or Matt Ferguson. Matt, I believe, is a postdoc now in Europe, and ask them to give you a talk on this work, because it's technically very sophisticated, and I cannot do it justice, in the little time that I have. But the key story is that, look, there is current flowing into the bulk, and it's very clear to me from this paper. And it's a bit more complex than that. If you take line cuts of how the current distribution is and how it changes as a function of the chemical potential as you backgate your device, you find that these current flows take on different kinds of patterns. So, in some region of the chemical potential, the current is flowing everywhere in the sample, and on the other hand, if you go further away, like in the top plots over here, you see that it's sort of splitting up into edge-like flows. And Matt Ferguson, the student, did a beautiful job in sort of using the top gate dependence of the equilibrium magnetization to argue that this is really mapping out the way the compressible and incompressible regions develop as you take your chemical potential from near the valence band up into the conduction band, as you take it through that magnetic gap. So I think it's very interesting work, and I think it's showing us that if we're going to rely on our theorist colleagues to tell us something about designing samples, they need to take some of these things into account. Incidentally, at the time that Katya and Matt were showing this data, David Goldhaber started talking to us, and they had some data, just purely electrical transport data, that had been sitting around for some years. This is Ilan Rosen's work. And then they realized that, well, they could interpret all of their data by assuming that with a model that says that, look, the current is flowing, in the bulk of the sample. And this is just by doing, measurements very systematically as a function of different contacts, and then matching it with simulation of Laplace's equation for a uniform sigma XX, right? So current flowing through the bulk. So I know that there are people in this field, including Charles Gould and Lawrence, who will have arguments with some of this, but I think that it's something very much up for debate and interesting for the consortium. Now, let me just finish off with a couple of other examples where I think this consortium might be interested in different kinds of materials. So some of you may remember this kind of a paper that Suezu and myself and Moses Chan and Lawrence Molenkamp published some years ago. This was a paper where we were trying to take a quantum anomalous Hall insulator, interface it with a superconductor, and try to verify some results that had been published in a prominent paper earlier. And we showed that, that there were there was no evidence for chiral Majorana states and all that. The idea basically was that we were unsuccessful. It was a failed search for chiral Majoranas, and one of those unusual times when a failed condensed matter experiment makes it to a good journal. But it raises the question: are there other avenues to integrate topology, ferromagnetism, superconductivity to go after some of these interesting topological kind of states, such as chiral Majorana states and so on? So Suezu, and this is Suezu Chang's idea, not mine. he came up with this idea. He said that, look, something like a decade ago, there was a very interesting paper published by a group in Hong Kong that if you grow iron telluride, which is an antiferromagnetic metal, and you grow bismuth telluride on top, you get a superconductor. So neither iron telluride nor bismuth telluride is a superconductor by itself, but you interface them and you get a superconductor. So we had this postdoc, Hamian Yi. He decided to reproduce this experiment, but reproduce it in a way where he could change the chemical potential. So he grew bismuth, antimony, telluride, iron telluride. Here is the ARPES data taken in our facility. And then on the right-hand side here, you see the resistance versus temperature, showing the superconducting transition, right? And this is a nice paper in which we've tried to make a case for why, as you change the chemical potential, the TC changes as it does, and so on. But then Shwezu came up with this interesting idea. He said, look, this is working with bismuth antimony telluride. What if we make the bismuth antimony telluride a ferromagnet, a quantum anomalous Hall insulator? So, I didn't think it would work, honestly, but, Hermione was a brave postdoc. He said, okay, I'm going to grow lots of samples. So he grew these samples where he grew bismuth antimony telluride doped with chromium under the conditions where if you simply grow it on strontium titanate, you would get the quantized anomalous Hall effect. But instead, he grows it on this iron telluride. And indeed, at temperatures like above 10 Kelvin, you can see a anomalous Hall effect. Now, of course, it's not quantized because there's a metal underneath, right? That's shorting and all that. But interestingly, if you lower your temperature further, you then get a transition to a superconductor, right? With Xiaodong Xu at University of Washington, we did some reflection MCD measurements, which showed that even as you go down to very low temperatures, where the sample is superconducting, you can see an RMCD hysteresis loop. Now, this is, of course, measured at the top of the sample, right? So presumably the superconductivity is happening at the interface. You're looking at the ferromagnetism at the top of the sample, and you see ferromagnetism, well below TC. And in fact, you can also see this with a low temperature magnetic force microscopy, and you can see, you can see the existence of ferromagnetism and ferromagnetic domains, down to where the sample is actually superconducting. But this doesn't answer a simple question. Do the superconducting and ferromagnetism actually coexist spatially? Because you can imagine that what's happening simply is that you have superconductivity here, and then somewhere up here you have ferromagnetism, and they have nothing to do with each other, which is interesting, but not particularly interesting. So Shwezu fortunately managed to get a scanning tunneling microscope, a Unisoku scanning tunneling microscope installed in the meantime, and carried out scanning tunneling spectroscopy, and actually shows that you do get actually a gap at the surface. Now, presumably this gap is due to superconductivity, and one can make arguments that you can get gaps developing in the STM for all sorts of reasons, right? But I think he's made a strong case that this is actually a superconducting gap. And so, so the idea here is that here's a new material for the community. We now offer this as a material within our consortium for people who are interested. We can grow samples, to your design and so on. We do the ARPES characterization. We do all the relevant characterization before you get the samples, right? And so I won't go into all the details. You can read it in this paper here because I'm taking up a bit too much time. But we have some, model theory to try to explain the data and so on. I think it's quite interesting. It's interesting that you take a material that's an antiferromagnet, you take a material that's a ferromagnetic quantum anomalous Hall insulator, put them together, and you get superconductivity. And the superconductivity is such that it proximatizes the entire ferromagnetic topological insulator right up to the surface. And this is over lengths of something like 10 nanometers or so. Finally, I just want to address one other class of materials where it's not immediately obvious that a consortium like yours should be interested, but maybe there are interesting ways to go. As you all know, or perhaps know, there's a great deal of interest in the condensed matter and spintronics community in these objects called skyrmions. These are topological spin textures in real space. And the spintronics community, of course, has been pursuing these with uh, sort of conventional materials like iron on iridium, iron palladium on iridium, and so on. And they do imaging. They also you can reveal the existence of these skyrmionic states by using anomalous Hall effect measurements. Um, and these are an interest for spintronics, for memories. There are also interesting proposals in the context of quantum technologies. So one of the ideas that we had explored a few years ago was, what if you put a topological insulator on an insulating ferromagnet? Then can you get these skyrmionic structures emerging at the interface? And in the transport, in this paper in Nano Letters, my colleagues and I were able to argue that the transport is strongly suggestive of the existence of these skyrmions. And this happens because of the spin-orbit coupling and the Dirac states. Now, we do not have imaging. So, I can honestly say that there is a possibility that this is still, the transport may still be due to some, funny artifacts. And the Würzburg group has talked about the kind of artifacts that can emerge, and so have we. Um, but it's a very interesting idea. The idea is that you take barium hexaferrite, which is an insulating ferrimagnet, and you grow a topological insulator on top. So you can imagine that what if we now grow a quantum anomalous Hall insulator on this barium hexaferrite, right? That would be an interesting thing to explore. And we're certainly working on this. Another idea that came to me a few years ago was, what if you take a topological semi-metal? The canonical example is cadmium arsenide. It's a Dirac semi-metal. We can actually grow it very nicely by MBE. It's high mobility, mobility in the something like a meter squared per volt second or greater. We can see beautiful RPES, showing these surface states. And also we see nice quantum oscillations, and we've done careful studies of the quantum Hall effect in these materials. And Suzanne Stemmer at UCSB has, of course, published a lot also in this area. And what I got interested in is, can you grow cadmium arsenide, this Dirac semi-metal, on a ferromagnet? Now, one would want to have a ferromagnet that doesn't short the current, right? So when you're studying quantum transport like this, you don't want your current to be flowing in the ferromagnet. So we tried growing on insulating ferromagnets, but just couldn't get it to work. And then I went back to my old background in manganese-doped 3,5 semiconductors, and said, what if we take a 3,5 semiconductor, put very little manganese in it so as to make a ferromagnet that's highly resistive, then can you do interesting things? And we can indeed grow very nice heterostructures. So here is a TEM image of manganese-doped indium arsenide with cadmium arsenide on top. And you see a nice, heteroepitaxy. And what happens here is that you actually form like, a PN junction in which by top gating and applying a bias and all that, you can turn the ferromagnetism on and off. But equally interesting, you can also get signatures of what may be, and emphasize maybe, a topological Hall effect due to skyrmions. Again, interest here is, can we image these? Can we get actual visual evidence for these objects? And we don't have that yet. Now, why is this interesting for metrology? Well, it turns out that we can grow cadmium arsenide in a particular orientation and geometry where, if the cadmium arsenide is thin enough, then it becomes a topological insulator rather than a topological semi-metal. And in that case, you now have, unlike the chromium-doped bismuth antimony telluride, you now have a high mobility material. in which you have these Dirac states, and you can proximatize magnetism perhaps by growing in an appropriate ferromagnet. So this is something that I'm very interested in discussing, pursuing. We are trying to do it ourselves, but we would love to collaborate with other people also in this context. So I won't go into all this, the details of the cadmium arsenide anymore because I'm sort of out of time. But I hope I've given you a good overview of what are the resources within our material synthesis community at Penn State, and given you a few examples that hopefully entice your interest. And I'm happy to discuss further. And thanks very much for your attention.